Today we're going to talk about parametric equations and sketching plane curves that the parametric equations represent, and also converting those equations to rectangular form. What are plane curves and parametric equations? If f and g are defined on some interval I, then the set of points f of t, comma g of t is a plane curve, and the equations x equals f of t, y equals g of t are the parametric equations for the curve with parameter t. Okay, so basically you have an equation that gives you the x part of the point, you have an equation that gives you the y part of the point, you plug in the same number into each equation, you got an xy pair, and so on. Sketch the curve defined by the parametric equations. So I'm going to build a table, but instead of your typical xy table, I'm going to build a txy table. So x is t squared minus 3t, and y is t minus 1. I'm going to first plug in your typical -2, -1, 0, 1. So to do that, we plug in, if t is -2, then we plug it in for t in the function. And that would be 4 plus 6 equals 10. Okay, and then when we plug in -2 for t here, we get -3. Okay, so that's our first, currently our first point, the smallest value for t, so our first point. Keep plugging those in. Okay, so let's graph what we have so far. At t equals -2, we have the point 10, -3. That's when t is -2. Okay, so it looks like we have this sideways curve, perhaps a parabola. So let's plug in just a few more values for t. I'm going to plug in 3, 4, and 5 to kind of get a fuller picture of this parametric curve. So here's a fuller picture of the curve, and I'm going to complete the points. Connect them. So how are parametric equations different from the rectangular equation that this represents? Because it could just be represented by a regular sideways parabola equation. So how does it differ to have parametric equations? Well, rectangular equation gives you a set of xy points that satisfies the curve. But parametric equations don't just give you those points, but it gives you the order in which you trace those points, okay? Many math problems call it the particle motion, particle moving across a curve, okay, moving along a curve would be, they use parametric equations for, to show the direction, the speed in which you trace out this curve, which is cool. It gives you more information. What if you used, instead of plugging in an integer value, plugged in some sort of expression for t? Well, I tried plugging in -t for t and getting two other parametric equations, and then I plugged in 2t for t to get two other parametric equations to see what kind of curve they gave. These are the two new parametric equations, the two new pairs, I guess. So in the first one, it actually has all the same points as the one we did above. I've highlighted the points that the original parametric curve shares with the two new ones. Same points, except the smallest value of t that I plugged in was -5. That means that's the starting point, okay? So we started before in our parametric curve. We started, first of all, down here, and the direction that our curve went that our trace was all the way up and around. But here we start up and we go down and around, or around and down. When I plugged in 2t for t, I had to plug in far fewer values in order to get common points with the previous curves. It was as if it was the same curve, but there's just less points, okay? As if it didn't take as many parameters to get a full picture of the curve. The curve is the same, but traced out in the opposite direction when we plugged in negative t. For plugging in 2t, the curve is the same, and so is the trace direction, but it is traced out, quote, twice as fast. Thus, parametrization contains more information than just the shape of the curve. It also indicates how the curve is being traced. So for our next example, we're going to convert parametric to rectangular by eliminating the parameter. It helps to find ways to write one in terms of the other using some sort of substitution or some sort of identity. So I'm going to start off by writing this equation in terms of t. Y plus 1 is equal to t. Now I'm going to substitute that in for t in the x equation. Y plus 1 squared minus 3 times y plus 1. Go ahead and distribute. Combine like terms, and you get the rectangular equation for the parametric curve that we traced in problem number 1, also seen right here. Now we're going to convert and then sketch the curve. First of all, when it comes to trigonometric equations as part of our parametric equations, we need to think about the restrictions and how that's going to affect the rectangular graph. For example, cosine of t is never less than -1 or greater than +1. Now, sine of t also has those same restrictions. This is excluding transformations. This is just the parent function. Okay, that means that for the rectangular equation, I will have the following restrictions. X has to be between -1 and 1, and y needs to be between -1 and 1. If the equation does not satisfy these restrictions, I need to impose these restrictions in my answer, include them in the rectangular equation, with the rectangular equation answer. So how can I relate cosine and sine? Well, I guess a very popular identity relates these two, as in cosine squared t plus sine squared t equals 1, the Pythagorean identity. Now, if x is equal to cosine t, that means cosine squared t is the same as x squared. Sine squared t is y squared, and that's equal to 1. This is our rectangular equation. Now, what does this look like? Oh, this is just the unit circle. All the points on this curve satisfy the rectangular equation x squared plus y squared equals 1. And x does not go outside of -1 to 1, and y does not go outside of -1 to 1. So you don't need to include that in the part that you box in. Okay, that's already within the restrictions of this rectangular equation. Now, which direction is the trace going? Okay, so I want you to draw arrows on your graphs, even if it's not included in the answers. And to do that, I'm going to check just the first two values of t and to get the direction. So I'm going to plug in 0 and pi halves. Cosine of 0 is 1, sine of 0 is 0, cosine of pi halves is 0, sine of 0 is 1. So the trace, or the particle motion along the curve, starts at 1, 0, and then goes to 0, 1. So which direction are we going in? We are going counterclockwise. And our last one, convert and then sketch the curve. Okay, let's talk about our restrictions. We have the same ones for x as above. Then I used Desmos to graph this function for y, and the restrictions for this function, the amplitude is like 1/2, and it only goes between 1 and 2. So the restrictions for our y value would be between 1 and 2. Okay. So can I write one in terms of the other and then substitute? That's what I'm going to try to do. Instead of cosine squared t, I'm going to write 1 minus sine squared t. The Pythagorean identity, distribute. All right, y is equal to 1 plus sine squared t. X is equal to sine t, which means x squared is equal to sine squared t. So our rectangular equation is y equals 1 plus substitute x squared. A parabola. All right, now this is where the restrictions are very necessary, because a parabola, the domain goes on forever and ever, but you see, our domain is not going to go on forever and ever. Let's go ahead and graph that. This is a parabola with vertex at 1, 0, so it has been vertically shifted once. 1 unit to the right, we rise 1. 1 unit to the left, we rise 1. And we don't go any further than that to the left or the right. Now, that's because of these restrictions. So we have to include these restrictions in our answer. It was necessary to see how the graph actually looked. Okay, but do we need to include the y restrictions? No, because if you restrict the domain, the y is automatically already restricted to that, right? It's not going to go below 1, and it's not going to go above 2. So it's already restricted. And then, because these are parametric equations, we get to know the direction that the trace is going, okay? But since this is going to continue kind of going between these 2 points, you're actually going up to this point, and then you kind of have to turn back around, kind of like a pendulum. You could always check this with a table by plugging in a few values for t. And that's parametric equations.